where we're going to dive straight into some seriously wild microscopic mysteries of human biology. Today, we're discovering how our skeleton functions, not just as this static support system, but as a highly advanced, self-assembling smart material. We're looking at some groundbreaking research that completely flips how we view bone formation, and it actually uncovers a hidden electrical network operating inside you right this very second. Okay, let's jump right in. To really grasp what's happening inside our bodies, we kind of need a perspective shift. Rather than viewing our skeleton as a dry, rigid frame, kind of like the wooden studs inside a house, we really have to look at it through the lens of engineering. Like this quote from the research points out, bone is a dynamic, adaptive, smart material. It's actively remodeling its own internal architecture all the time, swapping out old tissue with new bone just to adapt to the physical stress we put on it every single day. So if we zoom way in from the whole compact bone at the top all the way down to the microscopic collagen fibers at the bottom, we can see the foundational scaffolding of our skeleton. This freshly formed matrix is mainly made of soft type 1 collagen. Now, obviously, for our bones to be strong, our body has to somehow reinforce this soft, squishy scaffolding with hard minerals. And that reinforcement process, it happens at the unbelievably tiny scale of the tropocollagen matrix you see right there at the bottom. Section 1, the mineralization mystery. This brings us to a massive physiological puzzle that's had scientists scratching their heads for years. Here is the absolute crux of the mystery. We know that minerals, specifically these net-charged mineral clusters called amorphous calcium phosphate, or ACP, need to infiltrate tiny, specific gaps in the soft collagen to make the bones strong. But how in the world do they know exactly where to go? I mean, it's literally like trying to build a brick wall by just throwing mortar at it and hoping it magically lands perfectly in the joints. There had to be some underlying driving force pulling those minerals exactly into those intrafibrillar gaps. Section 2, the piezoelectric hypothesis. To finally solve this puzzle, researchers introduced a pretty radical suspect for the driving force behind this microscopic construction site: electricity. Let's define that real quick. Piezoelectricity is an inherent property of certain materials where they actually generate an electrical charge in response to applied mechanical stress. So the scientists hypothesized that our soft collagen exhibits piezoelectricity. What does that mean for you? It means that the everyday mechanical stress of just moving, running, or walking literally generates tiny electrical currents right inside your bones. Think of this piezoelectric electricity as a hidden electrical map. Actually, scratch that. It's more like a series of tiny magnets. If you look at the red wave in the middle, representing the piezo response, the hypothesis is that specific gap regions in the wavy collagen structure generate a naturally higher electrical charge when they get stressed. And because those mineral precursors we just talked about have a net electrical charge, this local surface potential acts exactly like a magnet. It pulls the minerals right into the gaps where they're needed to stiffen the bone, syncing up perfectly with that green wave showing mechanical stiffness. Section 3, clues from brittle bones. Now, a hypothesis is just a guess without proof, right? To prove this invisible electrical map actually exists and is essential, the researchers needed to find a broken map to interrogate. So they turned to osteogenesis imperfecta, which is commonly known as brittle bone disease. In this specific model, the condition is caused by a genetic mutation in the type 1 collagen, and it leads to bone fragility, decreased strength, and totally abnormal mineralization. The researchers figured, hey, if healthy bone relies on a precise electrical map to place minerals, and this diseased bone is brittle because its minerals are disorganized, well, then the brittle bone's electrical map must be broken. To test this out, they used something called resonance-enhanced piezo-response force microscopy, or PFM. It's this incredibly sensitive nanoscale tool where a conductive cantilever tip scans across the collagen matrix, literally poking it, applying mechanical stress and reading the minute electrical signatures that bounce back. It basically allows the scientists to see the electrical map. Section 4, a broken electrical map. And wow, the results from these microscopic interrogations provided exactly the smoking gun the scientists were looking for. We've talked a lot about the theory, but let's actually look directly at the scans from the PFM tool. We're going to compare healthy wild-type bone, or WT, against the brittle bone of osteogenesis imperfecta, or OI. Just look at the stark contrast here. In the healthy bone on the left, notice that gorgeous repeating lattice pattern in the bright yellow PFM amplitude map. That is a clear repeating pattern of high and low electrical amplitude. It's a perfect set of instructions. But then look at the brittle bone scan on the right. Even though the physical height structure looks kind of similar, its electrical signature is an absolute mess. It's scattered, it's random, and there is no clear map at all. And the numbers starkly confirm what our eyes are seeing. In healthy bone, researchers measured a massive 55% stronger electrical response in the specific gaps where minerals need to go compared to the overlapping regions. It's a very distinct magnetic-like pull. But in the brittle bone, there was no statistically significant difference in the electrical response between the regions. The map is just completely flattened out. The crucial point is laid out right here in the data. The red bars represent the gaps, and the blue bars represent the overlaps. In the healthy bone on the left, you see a massive distinct difference. But in the brittle bone on the right, the bars are practically identical. And because the brittle bone lacks this targeted, localized electrical pull, the charged minerals just infiltrate randomly. They don't fill the gaps efficiently at all, causing the bone to lose that complex mechanical structure that normally makes our skeletons so incredibly resilient. Let's move to a wider view for a second, just to see how this builds up at a slightly larger scale. Zooming out, the researchers noticed another vital difference. In the healthy collagen on the left, the fibers align perfectly in one direction. This ordered alignment lets them pool their individual electrical forces together into one strong, unified piezoelectric effect. However, the brittle bone fibers on the right are totally chaotic and misaligned. And because they're misaligned, their weak electrical signals scatter and actually cancel each other out, which just further cripples the bone's ability to properly mineralize. Section 5. Building better bones. Understanding this verdict, that electricity fundamentally drives the precision of bone formation, has absolutely massive implications for the future. Here's one final fascinating detail for you. When they scanned fully mineralized bone, so bone that had already finished its construction project, the electrical signal was very weak. The strong electrical map only showed up when the bone was demineralized. This tells us that this piezoelectrical map acts as an essential spark, specifically during that initial, primary phase of bone building. It guides the very first wave of minerals into place before the scaffold gets fully covered, and the electrical signal is naturally dampened down by the hard minerals. So why does all of this matter to us? Well, by successfully decoding this natural, smart electrical blueprint, we're opening huge doors in multiple fields. For engineers, understanding how collagen uses electricity to self-assemble hard minerals means they can go on to design infinitely better bio-inspired, self-repairing synthetic materials. And for doctors, it means we finally understand the specific localized failure in devastating genetic conditions like osteogenesis imperfecta. It paves the way for targeted therapies that could one day actually restore this broken electrical map in patients. The sheer brilliance of human biomechanics is just profound. We walk around every single day, applying mechanical stress to our frames, completely unaware that our skeleton is translating those literal steps into an electrical map that physically rebuilds our foundation. It really leaves you wondering, doesn't it? If our bones are this advanced, what other microscopic mysteries and smart materials are operating inside our bodies at this very second? Thanks for joining me on this explainer, and stay curious.